Okay, good evening, everybody, and welcome to another organic chemistry session. Before we start the session today, just a couple of announcements. Tomorrow there will be another online review session, and for that session, we are going to use the previous class exam for the session tomorrow. So that will be 8 o'clock tomorrow, October 17th, 8 o'clock tomorrow. So I will remind you tomorrow and send you the link for those of you who may not have the link. And also do not forget that the second class exam, is scheduled for next Thursday. That is October 18th. This Thursday, October 18th, right? Next Thursday, October 18th, right? Okay. So now let us get going with the class. We do want to finish with the chapter 8 today, and hopefully I should finish chapter 8 within the next 30 to 40 minutes, and then we'll spend the rest of the class to solve problems or answer questions from you guys. Okay. If you recall, when we left on Tuesday, we showed you the various ways in which we can cleave a carbon-carbon double bond. And we titled this as oxidative cleavage of alkenes to give carbonyl compounds. We told you that if we take this reagent here, which is ozone, followed by zinc in some acid medium, we will cleave a carbon-carbon double bond such that each of the carbon-carbon double bond becomes a carbonyl, just as you see here and here. Okay. And of course, another example is here, in which if we cleave this, here we get this part of the molecule become this part. You notice here, whenever the carbon of the carbon-carbon double bond is attached to an hydrogen, what you get becomes the carbonyl of an aldehyde, which is what you have here. And similarly, you also have a carbonyl of an aldehyde here, which is this part of the molecule. Now, what I want to give you now is I want to give you two more reagents that will allow you to cleave or split a carbon-carbon double bond. Two more reagents. So my advice to you is, at this point, you want to begin to make up a table of reagents and say exactly what the reagents will do, because that will help you in actually following all of the series of reagents we are going to be using for the rest of the semester. So let me give you two more reagents that we could use to cleave a carbon-carbon double bond. So we're going to have this cleavage of carbon-carbon double bond using potassium permanganate. Now, if you take this molecule here, okay, this carbon-carbon double bond, and we have potassium permanganate. This is potassium permanganate here. Okay, MnO4 in step 1, and then we follow that up with Actually, this should be together with hydronium ion or some kind of dilute acid. So what you have, you will cleave this carbon-carbon double bond so that this carbon here becomes the carbon of a carboxyl group if this carbon is attached to an hydrogen atom. Similarly, this becomes the carbon of a carboxyl group if this carbon is attached to an hydrogen atom. So in this case, what do we get? We get this molecule here. We get a dicarboxylic acid. Now, supposing I simply just gave you this reagent here, I gave you this reagent here, and also gave you this product here, and I ask you to give me the starting material. That is the kind of question you should be expecting. Okay? Just taking a look at this product here and the reagent, you should know that what this reagent will do is to cleave a carbon-carbon double bond so that each carbon of the carbon-carbon double bond becomes a carboxyl group. So in this case, if I simply gave you this molecule here, this product, and I say, give me the starting material, if I do not give you this, what you will do is say, okay, this here, this carbonyl of the carboxyl group must have been the original carbon-carbon double bond, right? That's the way I will look at it. And then I will say, okay, if that is the case, so you have this double bond here, and then you ask yourself, in this case, how many carbons do you have in the ring? I will say, okay, this is carbon 1, 2, 3, 4, 5, 6. So that tells you that is a 6-member ring, which is what this is. Yes. Yes. Remember what we told you. What this reagent will do is to cleave this carbon-carbon double bond so that this carbon now becomes a carboxyl group. And that is what you have here. This is a carboxyl group. And this is a carboxyl group. So that OH is a result of that reaction. It wasn't there before. Okay? Yes? So that it will be more obvious? Okay, the question is, can I draw it another way? Yes, you could draw it in a way that it will look very obvious to you. For example, supposing we have this. Supposing we have this. If we have this here, and we have this here, and we have potassium permanganate. In acid medium. Okay, what do you think the product will be? What would be the product? Okay, what happens? What does this reagent do? Can you say it in your own words? It will cleave this, right? Okay, but now, because this carbon here is not attached to an hydrogen, this carbon now only becomes the carbonyl of a ketone. And this carbon becomes the carbonyl of a carboxyl group. Okay, so the product will be, okay, let me draw this the way Paris said we should draw it so that it looks obvious. Okay, so we now have, right? Are you okay with that? Okay, now we have Okay, does that look obvious to you? Okay, so now in this case, we split this carbon-carbon double bond to a ketone and a carboxyl group. Okay, and that is because on this carbon here, there is no hydrogen attached to this, so that becomes the carbonyl of a ketone. Now, supposing we have this. What will be the product of this reaction? Potassium permanganate in acidic medium. What will be the product? What will be the product? How many molecules do you think we are going to get here? 2 molecules, right? And both of them will be what class of compound? Carboxylic acid. Both of them will be carboxylic acid. Because here, you clip this become carboxyl group, and this become carboxyl group. Because each one of those carbons is attached to an hydrogen atom. Okay, so what do we have? We have this product here. Plus, and that is this fragment right here, plus this product. Now, in another example, to finish writing, okay, in another example, supposing we have this. Yes. I'll give you one more second. Okay, so you see here, essentially what we are doing is splitting the carbon-carbon double bond. Okay, to get, in this case, 2 carboxylic acid. Okay, in another example, supposing we have this. In this case, you have a terminal carbon-carbon double bond. In other words, the carbon-carbon double bond is at the end of the chain, in which you have this carbon is attached to 2 hydrogen atoms. In that case, what is going to happen, you are going to clip this. This becomes carboxyl group, and this carbon here becomes carbon dioxide. Okay, so this is what you get. Plus carbon dioxide. And that carbon dioxide is coming from this carbon here. And that is in the case in which you have the carbon-carbon double bond at the end of the chain. Okay, supposing we have this. Yes. The hydrogen is gone as part of the reaction. That is what this reagent will do. Okay? This hydrogen here? Where? Which hydrogen? This here? This here? Yeah, it is gone because this carbon here is completely oxidized to carbon dioxide. Okay, so whenever you have the carbon-carbon double bond, it's at the end of the chain, in which one of the carbon-carbon double bond is attached to 2 hydrogens, then that carbon is oxidized to carbon dioxide. Okay? Okay, so what will be the product of this reaction here? Can anybody tell me what will be the product of this reaction? What is it? Cyclohexanone, right? You cleave this becomes a ketone, and this becomes carbon dioxide. So therefore, supposing I did not give you this molecule here, and I just call this compound A, and I give you this reagent, and I say compound A reacted with this reagent to form cyclohexanone plus carbon dioxide, and then I say write the structure for compound A. You should be able to do that very easily. Supposing I did not give you this starting material, and all I did was give you the reagent. You should know what this reagent will do, and then I gave you this product here, cyclohexanone plus carbon dioxide, and I say give me the structure, write the structure of compound A. So you should be able to reconstruct compound A based on the product of the reaction. Okay, now, so far now we have two methods for cleaving or splitting a carbon-carbon double bond. Now I will now give you the third method. I'll say cleavage of carbon-carbon double bond via hydroxylation and periodic acid oxidation. Now, what do we mean by that? I could take a carbon-carbon double bond and react the carbon-carbon double bond with this molecule here, osmium tetroxide. That is step one. And you follow that up with sodium hydrogen sulfide. What this reagent will do is to form this molecule here. So what has this reagent done? Can you tell me exactly what has this reagent done at this point? It added two hydroxy group across a carbon-carbon double bond. Okay? So what this reagent has done, osmium tetroxide, what does it do? It will add two OH groups across a carbon-carbon double bond to form single bonds. And it will do it in such a way that the two OH groups will be cis to each other. Okay? So therefore you form the cis product. This type of reaction, in which we add two hydroxy group to the carbon-carbon double bond, is called hydroxylation. Okay, and also, because the stereochemistry here is a cis stereochemistry, we say this is a stereospecific reaction. Because we only form one stereoisomer, the cis isomer, not the trans isomer. Okay, and that is what this reagent will do. Yes, go ahead. Because, say that again. It is stereospecific because we are only forming one stereoisomer. In this case, the cis stereoisomer. We do not form the trans isomer. Oh, it's not syn, you said? Yeah. Well, okay, therefore, very good. Therefore, we refer to this reagent as a syn addition reagent. We say it is a syn addition, which is the same thing as cis addition reagent. So we refer to the osmium tetroxide and any other reagent that will add any kind of groups cis to a double bond in such a way that the product will be cis. We refer to them as syn addition reagents. Okay, so this is a syn addition reagent. In some books they use syn, and in some books they use cis. So cis and syn are basically the same. Now, what do we do with this? Remember, we told you that we want to use this to cleave the carbon-carbon double bond. So now you could now take this you now take this and you take iodic acid, iodic acid, okay. And then you, step 1, you follow this always. Dilute acid, and you get this product here. Sorry. You are going to cleave the carbon-carbon, this here, this single bond here. You will cleave it, so now you now form this product. You notice there is a similarity between this reaction and the ozonolysis. Okay? In other words, if we started with this, remember we started with this. Step 1, osmium tetroxide. And step 2, sodium hydrogen sulfide to form the what we call the 1,2-diol. We say 1,2-diol because it's almost as though we have two alcohols. and the two hydroxy group are in a 1-2 relationship to each other. Okay, so once you form the 1,2 diol, then you will now take the iodic acid to cleave this bond. So the net effect is this carbon here becomes the carbonyl of an aldehyde, and this other carbon becomes the carbonyl of an aldehyde. However, that is because we have hydrogens attached to those carbons. Supposing we have this. Supposing we have this. Supposing we have this. Say step 1, osmium tetroxide. Step 2, sodium hydrogen sulfide. And then we say step 3, we add the iodic acid. Now, what will be the product? What will be the product? What class of compound are we going to get? What class of compound? Is it going to be carboxylic acid, aldehyde, or ketone? What class of compounds are we going to get? What is it? Carboxylic acid. Oh yeah? Do you think so? Keep in mind the iodic acid will cleave to give you the aldehyde. Whenever you have an hydrogen attached to this carbon here. And then if you do not have hydrogen attached to that carbon, it becomes the carbonyl of a ketone. Very similar to what you get with ozonolysis. Okay? So in this case, you get this product here. Okay. So now we have 3 methods for cleaving the carbon-carbon double bond. One is ozonolysis. The second one is potassium permanganate in acidic medium. And the third one is a combination of reagents in which you use osmium tetroxide to do the hydroxylation, followed by cleavage with iodic acid. Okay. So at this point, I also want to, since we started with hydroxylation, I want to also give you additional reagents that will allow you to do hydroxylation. Let's call this other reagents for hydroxylation. If I have this, and I have this reagent here, we call this M-chloro R benzoic acid. Now, for in the future, you don't have to write this structure. You could simply do MCPBA instead of writing the structure here. Just write MCPBA, that is M-chloroperbenzoic acid. Now, what this reagent will do is to add oxygen to the carbon-carbon double bond to form a 3-member ring. So you form this. Okay, this product here is what we call an epoxide. We call this an epoxide. The 3-member ring in which you have one of the ring member is an oxygen atom. Okay, we call an epoxide. And the process of making an epoxide we refer to as epoxidation. I told you we are going to learn organic language. By the time we finish, you guys will be organic chemists. Okay, this is called epoxidation, which is the process of forming an epoxide. And one of the few reagents that will allow us to do that is M-chloroperbenzoic acid, MCPBA, this reagent here. Now, if you now take the the epoxide, to take the epoxide, you add dilute acid to it. The epoxide will open up such that you now form a 1,2 diol This time, the 1,2 diol, the 2 hydroxy group, will be trans to each other. This is hydrogen, of course, hydrogen. So therefore, to form the trans product, trans 1,2 diol, trans 1,2 diol, so therefore, the combination of these reagents, if I have this, do you want me to go back? So the combination of the M-chloroperbenzoic acid followed by dilute acid, what it does is to give you the addition of 2 hydroxy groups to the carbon-carbon double bond, such that those 2 hydroxy groups will be trans to each other, which is the opposite of what you get with the osmium tetroxide. Okay? Okay, so therefore, if you have this, we have M-chloroperbenzoic acid. Step 1. Now, if you just want to go directly to the diol, if you do not want to stop at the epoxide stage, you could simply just combine the two, the MCPBA, with followed by hydronium ion, And then what do you get? You get the trans 1,2-diol. Okay. Trans 1,2-diol. Oh, I'm sorry. This would be CH. Let me write it better. Okay, so now we have given you two methods for hydroxylation. This is also a process of hydroxylation. So if I ask you what is hydroxylation, what is hydroxylation? Adding two hydroxy across a carbon-carbon double bond. That is hydroxylation. Okay? Yes. Yeah, the epoxidation is just forming the epoxide. If that is what you want to make, you could stop right there. Okay? But if you want to make the do a hydroxylation, then you add the dilute acid to go to the hydroxylation part of it. Okay? So those are actually two different reactions. The epoxidation followed by the acid hydrolysis to form the 1,2-diol. There's another way in which we could also make the 1,2-diol. Okay, let us see this synthesis of 1,2-diol via the halohydrin. Halohydrin. Remember earlier on we showed you how to form halohydrin, and what is that? If we have this here, and we have, let us say we take bromine or chlorine. Bromine water. Remember what we said? We had bromine water or chlorine water. What is the product we expect to get here? What will be the product here? What is it? Bromine and hydroxy added to the carbon-carbon, exactly. So in this case, what would be the stereochemistry? Remember that we form an intermediate bromonium ion. Okay, and then it will be trans. Okay, so now what you're going to get when you use bromine water or chlorine water, what you do, you are adding bromine and hydroxy group, bromine and OH across the carbon-carbon double bond, such that they will be trans to each other. In this case, you have bromine here, you have hydroxy here. They will be trans to each other. Okay? Of course, you have the hydrogen is here, and another hydrogen here. Trans to each other. Now, if you now take this bromohydrin If you now take this bromohydrin and you take sodium hydroxide or potassium hydroxide, in this case, what we really need here is the hydroxide. So, for the purpose of our presentation, let us simply just say all we need is the hydroxide. The sodium or the potassium, they really are there as spectator ions. The hydroxide could come from potassium hydroxide or sodium hydroxide. And what happens? The hydroxide will act as a base, come here, in an acid-base reaction, pull the proton from this hydroxy group, and then what happens, the electron that is going to be left behind will be used to attack this carbon here, and in so doing, kicking this bromide out of the molecule to form an epoxide. Okay? So we form an epoxide. So this is another way in which we could form an epoxide. So this is another way in which we could form an epoxide. So we could form an epoxide by performing the halohydrin reaction, in which we react bromine in water or chlorine in water with an alkene, a carbon-carbon double bond. That gives us the trans halohydrin, either bromohydrin or chlorohydrin. And then you now take sodium hydroxide or potassium hydroxide, react with the halohydrin to now form the epoxide. Now, once we form the epoxide, to form the 1,2 diol, what do we need? To form the 1,2 diol, what do we need? Exactly, just add adrenal ion. So now you could just do this, and that gives us and the product will be okay. Okay, so we could write this as a sequence of reaction. We could simply do this. We could do this. Okay? So we could do this. You say, step 1, in this case, let us use chlorine water, right? And then we say step 2, where they are coming from? We say step 1, we do the, let us use chlorine water, just people use chlorine or bromine, and then step 2, we say potassium hydroxide or sodium hydroxide, and then we say step 3, okay, so what does the step 1 do? What does the step 1 do? form the chlorohydrin with the chlorine and hydroxide on 1,2 carbon to each other, right? Then followed by the hydroxide, what does that do? It forms the epoxide, okay? And then finally the hydroxide will now open up the epoxide, okay? So now you have okay, we have 2 more reactions before we finish chapter 8, and then that will be it for chapter 8. 2 more reactions. Okay, now, so far, let us recap what we've done so far. We've shown you how to cleave the carbon-carbon double bond. We have 3 methods for doing that. One is ozonolysis. The other is going through hydroxylation and iodic acid. And then the other is what? What is the third method for cleaving the carbon-carbon double bond? We did that already. That's with iodic acid. Which one? What? No. Permanganate, potassium permanganate. Okay? So those are the 3 methods for cleaving the carbon-carbon double bond. Now we're also giving you, in this case, 3 methods for forming 1,2-diol, which is we call hydroxylation. What are the 3 methods? Osmium tetroxide, halohydrin, followed by epoxide formation, followed by hydroxylation, right? And then which is the third one? Give you the summary? Okay, let us summarize for you. Summary of oxidative reactions of carbon-carbon double bonds. One. Okay. We could do the cleavage. With ozone, followed by zinc, two, cleavage with potassium permanganate, in acidic medium. 3, cleavage via hydroxylation then iodic acid oxidation, then iodic acid, okay, now continue with our summary. Then we also have the method for hydroxylation. Okay, method for hydroxylation. osmium tetroxide, another one is halohydrin formation, followed by hydroxide, leading to epoxide, followed by hydrolysis, by hydronium ion hydrolysis, okay, what is the third one? Using benzoic acid, epoxidation, with benzoic acid, MCPBA, followed by hydronium ion hydrolysis. Okay, so I will now give you the last two reactions of alkene that we are going to deal with before we leave this chapter. Yes, go ahead. Yeah, osmium tetroxide, use of osmium tetroxide. So let me see here, just a minute. Let me go back to, do I have that here? Okay. This is the, I'll get back with you. This is an example of the epoxidation. You see that right here, using M-chlorobenzoic acid. You don't have to worry about this. This is the byproduct that you form. Our interest is on the epoxidation product. Okay, and of course, this is an example of the halohydrin that we gave you to form this here, and then followed by sodium hydroxide to form the epoxide. And then we open up the epoxide with hydronium ion to form the diol. You don't need to worry about this mechanism. I simply just want to show you for those of you who might be interested. Now, one of the last two reactions I want to show you is addition of carbon. Just so happens we could also add a carbon atom to the carbon-carbon double bond by using what we call a carbene. A carbene is a very reactive intermediate that can be formed by simply adding chloroform, this is chloroform right here, and potassium hydroxide or sodium hydroxide. What happens in this case, you form the carbene, in which carbene is a molecule that has only two groups attached to it, and then you have a pair of non-bonding electrons, very, very reactive species. And that simply just adds to the carbon-carbon double bond, and that is what you have here. So if you have chloroform in the presence of potassium hydroxide or sodium hydroxide, you get this kind of product right here, in which this carbon here, of course, is attached to two chlorine atoms. And those two chlorine atoms are here. In essence, what do we have here? One hydrogen and a chlorine atom is being kicked out of this molecule here to form this carbene. Once you form this carbene, this dichlorocarbene, and then that would then react with the double bond to form this product right here. So the way we will do this, supposing I think they just give you this. I say we have chloroform. And I say, what is the product? What will be the product? The product will be, you are removing one hydrogen from here and a chlorine from here, and then the dichlorocarbene that you form, which is this here, will simply add to the double bond. So here we form so what this reagent does is to simply form a three-member ring, which is a cyclopropane ring. In this particular instance, we have these two chlorine atoms right here, if you're starting with chloroform. Now, supposing we do not want the chlorine in there, we could use this reagent. Diiodomethane with zinc, amalgam, say zinc, which is simply just a mixture of zinc and copper. If you do that, what you get is this here. Okay, in essence, what this reagent does is to form the carbene, which is this here, and this carbene now reacts with the carbon-carbon double bond, and that is what you have here. So, in essence, the net process here is this reagent will add a carbon atom to a carbon-carbon double bond. This reagent will add also a carbon atom to a carbon-carbon double bond. In this case, you will have two chlorine atoms attached to that carbon. Okay, we are almost there, the last reaction. The last reaction now I want to show you how we make this here. This is a polyethylene or polypropylene. You guys know this when you go to the grocery supermarket to buy. Okay? So let us look at how do we make this that particular item. Last reaction we're going to call this free radical polymerization reactions of alkenes. Okay. In this process, there are three stages. The first stage is what we call the initiation step. The second process is what we call the propagation step. And the last step is what we call the termination step. Now what happens if you want, say for example, if you want this molecule here, which we call ethene if you use the IUPAC name, but the common name for that molecule is ethylene. If you want to polymerize that, polymerization simply means you start with a small molecule and you begin to grow the small molecules so they get bigger and bigger and bigger to the point where you begin to make plastics like this. Okay, so how does that happen? Let us go through the 3 steps. For this to happen, you start with what we call a free radical initiator, in this case, which is step 1. Free we could take any peroxide. Say for example, we could take your hydrogen peroxide. Most of you are familiar with hydrogen peroxide. Any molecule in which you have 2 oxygen atoms are attached to each other, we call this peroxide. We could take hydrogen peroxide and you apply light or just heat. You will break this bond in an homolytic fashion. Remember that most of the reaction we have been doing so far, we have been breaking bonds heterolytically. So here you could break this. 1 electron goes here, and then another electron goes here. So now you form what we call free radical. Okay? From free radical. Now we go to the next step. We have now started the free initiation step. The free radical that you now form for the second step, which is propagation, that free radical, we told you before, free radicals are very, very reactive species. Those are the species that, for the most part, cause our cancer in most of our organ system. So this is an intermediate that really we need to avoid as much as possible by watching our diet. Okay, so you have a free radical here. And then let us imagine that we have a carbon-carbon double bond. This time the carbon-carbon double bond of ethylene. What happens? This free radical here will react with this. So this will break the pi bond so that homolytically, so that this pi bond, if 1 electron comes here, reacts with that free radical, and then another electron will now come to this carbon here. You form this. Now the free radical is now on this carbon. And now what is going to happen? Another molecule of ethylene will come. Okay? That free radical that is now formed comes to react with this. One of the electrons in the pi electron system. Okay? This is the way we indicate one electron motion. In other words, whenever you have a fish hook arrow, that simply tells you that we are only moving one electron. Of course, the other electron will come here. And then what do we get? To form this product. And this process can continue as long as we have the ethylene in the system. So we could add another one. So now what do we have? We end up forming. So what we generally will do, we now have this. Let us put a bracket here, saying that we have some kind of N here, meaning that we have so many repeating units. This becomes your repeating unit. And N definitely equals to or greater than 100. Okay, so when you get the type of plastic that you want, you could now stop the reaction in what we call the termination step. Okay, once you get the kind of material that you want, you could now stop the reaction, and that leads to the termination step, which will be this here. Step 3. In the termination step, anytime you have any two free radicals come together, that terminates the process. Okay, so that would be, for example, if you have plus this here, okay, termination step is any two free radicals coming together, joining together. That is the termination step. So this could be your termination step. Okay? And that is how we form most of the plastic that you have in commerce today. This particular plastic we call polyethylene is what we call the polyethylene plastic, depending on the starting material. So when you go to the supermarket, they give you those plastic bags. Now you know what they are. And these materials are very, very unreactive. Keep in mind, what they really amount to is a long chain of alkanes. And we know that alkanes are very unreactive. And that is why they just pollute the environment. So what we need to do, begin to look for as chemists, I mean, you guys need to begin to look for biodegradable material, because these materials are not biodegradable. Okay? Okay, now, supposing we have this, then what time we have before we go to? Oh, wow. Huh? Supposing we have this. Supposing we have this. Okay, this is propylene. Of course, the IUPAC name will be what? What will be the IUPAC name for this? What would be the IUPAC name for this? What is it? Propene, exactly. The IUPAC will be propene. Okay, now supposing we have this. Some kind of peroxide, let us put peroxide here just to initiate the process. And I tell you to draw the structure of the polymer that will be formed. What do you think that polymer will look like? Okay, of course it will look like very much like this. You have this here. You have this here. The polymer will look very much like this. Now, why do I say that? Because what happens when you form the free radical that you form will be this free radical here. Okay? Because once the peroxide, the initial free radical comes in, reacts with this, you form a free radical on this tertiary carbon, on this secondary carbon. Just as in the case of the carbocation, the more substituted free radical are more stable than the less substituted free radical. In other words, the tertiary free radical is more stable than the secondary free radical, than the primary free radical, than the methyl free radical. So in this case, the initial free radical that will be formed will be this, and then this will continue to react with to initially form this. Okay? And that is the end of chapter 8. To do what? No. That is the end of chapter 8. So we will have the review session tomorrow. But I do want us to do, since we have 24, since we have about 6 more minutes, I want to throw this question at you tomorrow. I want to throw this question at you. Let me see here. Okay. Okay, just for you to think about this question here. Okay. Okay, Paris, can you read this question for us?
Undergoes reaction with dilute H2 as well as activity of the mixture of two alkenes the major alkene part of the ethylene hexagon after ozone treatment followed by a reduction of acetic acid. Draw the structure and complement.
Okay. So what we have compound A. This is what we call a roadmap question. We have compound A. The formula is C12H22 with oxygen. And then we say compound A reacts with dilute sulfuric acid, which means that we have water in there. Okay? To form compound B and C. Okay, and the formula here is C12H20. And the same thing here, C12H20, right? They've already told us compound A, compound B and C are alkenes. What is the index of hydrogen deficiency of compound A? What is it? Is it 2? Is it 2, right? Okay. So index of hydrogen deficiency of compound A equals to 2. So that means it may have two double bonds or two rings, right? Or a combination thereof. Now that you now have an alkene formed here, okay, it could very well mean that you have three double bonds, because the index of hydrogen deficiency for this B and C will be 3, since you have now done dehydration. This is dehydration right here. Now they've also told us that compound B, which is the major alkene, undergoes ozonolysis, followed by zinc, in some kind of acid. Take this out. Okay, undergoes ozonolysis to form cyclohexanone, only cyclohexanone. That is the key, right? To form only cyclohexanone. Okay, now the question is, what is the structure of A? Okay. The key to this, to answering this question, is to know what is going on here with ozonolysis. Compound B, with this formula here, C12H20, is now giving you this here, which is now C6, right? In other words, we also know that ozonolysis, what does ozonolysis do? It will cleave what? A carbon-carbon bond, right? Okay? So therefore, this carbonyl must come from a carbon-carbon, right? Double bond. And since we are starting with C12, H20, and we're ending up with this right here, what are we starting with? How many hydrogen here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's almost as if we're splitting that molecule into 2. So therefore, I would say compound B must be this. I would say compound B must be that. You see that? You see how compound B could come from, this compound here, cyclohexanone. You see how this cyclohexanone could come from compound B by splitting this. Right? Okay, so this is the key. So if this is compound B, therefore, what will compound A be? Keep in mind, compound A going to B is because of dehydration, right? It's a result of dehydration. So if it is a result of dehydration, that means compound A must be an alcohol, right? So the question now is, where is the OH group in compound A for this molecule? What will it be? If we are going to dehydrate A to get B, this is B, where would the OH be? Keep in mind that it's from two alkenes, B and C, okay? So, where will it be? If it was here, right? Could it be here? Is that possible? Why not? If it was here, you could form a double bond here, right? That could be B, right? You could then also form a double bond here. That would be C. But that would not be consistent with what you have here. So therefore, it has to be here. The hydroxy has to be here. So this must be compound A. Why? Because when you do dehydration, you form the double bond here, which is what you have here, and that is compound B, and they say that is the major product. And therefore compound B must be this here. So this must be C, compound C, and this must be compound B, okay, and this is compound A. This is the minor product because this is less substituted. No? None of you get it. Well, I just want to throw that out. I want to throw that out. Okay, but that is the kind of thinking. That is the kind of thinking that you have to get yourself into when you do this exam on Thursday. Okay. On that note, I will see you on Thursday. Oh, leave this? Okay. What? Before I leave tonight.
How can
Just a minute.
if you told us before that the